addressed all these pieces before, but we did not call them in terms of a calculus term. I want you to think back, and don't write this down, but I want you to think back. Remember, like October-ish, we were doing graphs where you had to find your maximums, your minimums, your inflection points, and all these things. We did your domain, your range, your intercepts. You did really well on all those graphs. Then we did a set of graphs that were rationals, and they had a fraction in them. And for instance, it looked like this. And we said there's a domain restriction here. It can't use anything in the denominator that would make it be 0, right? So in this case, we would not be able to use a 3 or a 5 in your denominator, true? So what we did first was we factored your numerator. You don't have to write this down. I just want to tie this together for you. And we said if there was a common factor, we took it out, and that became your point of discontinuity. Not a vertical asymptote, just a little point that it looked like the graph connected, but when we looked at your table, there was a little error there. And we said we could find your point of discontinuity by reducing this and then plugging in x is equal to 3. So if my point of discontinuity would be 3 plus 2 is 5, 3 minus 5 would be negative 2, would be 3 negative 5 halves. That would be the point where if I could fill this in, I would have a little point of discontinuity. The other factor that I couldn't get rid of became an asymptote. So, and then I checked my other asymptotes, and I would make my graph go like this. Remember these, that they kind of went in different directions because of the asymptotes? And when they jumped at the 3, we put a little circle here. Remember we put the little circle? And then we filled in your little circle, calling it a point of discontinuity. Well, today, we're going to address your point of discontinuity, as well as your points that exist in your graph, but we're going to address it with a limit. So instead of writing it like this, we're going to say as a limit as x approaches 3. So I can't plug a 3 in here, because the 3 minus 3 would give me 0. But I could plug in and get rid of this, factor this out, figure out what I'm missing, and then plug it in. But today, we're just going to look at the graph part of this. We're going to look at what would this point be if I could fill it in on my graph. Do you see what I'm saying with this? Do you kind of remember this a little bit? We're not learning anything new. We're just naming it differently. And we're using a concept, we used the concept of calculus, but now we're using the words for it. We're calling it a limit. As my x value approaches something, what would my y value be? Now sometimes my y value exists. It's there. That's my limit. Sometimes my y value doesn't exist at all. I could have a graph that approaches this way and approaches this way, and there's no way they're going to meet in the middle. And then we have something that's the limit doesn't exist. So we're going to spend a little time talking about continuous and not continuous. So unfortunately this note page you don't have, but they're kind of incorporated into your other notes. So all I want you to do to this one is just listen, so that you can understand where we're going with this. When we talk about continuous, if a graph is continuous, such as, remember your other graphs? These were continuous. We put our pens down, and we never pick our pen up. There's not one x value in there that I can't use. Then we did things that look like this. These were called piecewise functions. Generally, we had different equations, and then different parts of the domain where we could graph those. So if you recall, I had you make little tables. We kept an open circle and a closed circle, an open circle and a closed circle. And then we graphed our points. Sometimes they overlapped onto the same point. sometimes they didn't. Today we're only looking at the graphs of these. So if I have to ever pick my pen up, then it is not continuous. If I start here and I go here and I need to get to the other place, this is not continuous. I have to pick my pen up, start up, I gotta jump over that opening. This is good, that's good. So it's not continuous here, and it's not continuous here. Sometimes we get a little extraneous pieces. I'm not really sure what that open means over here, so just kind of ignore this little round circle. But this guy up here, all that's there for is so that we have a function. A vertical line test says every x has one and only one y value. So that does pass a vertical line test. In terms of my function itself, it's not helping my limit at all. I would have to jump up to that point. So there's certain times where we can make it continuous. For instance, if I come over here and I fill this point in, can I now be continuous right there? Then this point is called a removable point. Removable, or fill it in and I can go through it. This guy right here, there's no way I can connect that. That limit does not exist. There's no way to pull that piece together. That we call a jump discontinuity. We have a point of discontinuity where we could fill it in. We have a jump discontinuity where we can't connect it. Make sense? Kinda? Okay. Here's a little bit more. A continuity in a point, and this is going to give us a left and a right order. An interior point just means that, in the interior, in the inside. This guy is my interior point. It's inside this function. It's approached from the left and from the right, and it has a point where it meets. This is an endpoint. In an endpoint, we usually approach from a positive side, from a negative side. So I don't know if you can see it down here, but it says as x approaches from A positive. A positives, think of where your positives come from. They come from over here. So as x approaches the A positive, from the A positive side, as we're approaching the positive, it'll hit this guy here. I think the B is approaching from the negative. This guy's approaching from the negative. This comes from your negatives. Okay. This guy's coming from your positives. So that's kind of like putting into reference there. We're going to do a lot more of these, but I just kind of wanted to give you an overview first. Okay, and again, a removable point is your point of discontinuity. A jump discontinuity, and I think this is on your other sheet as well, does not exist. There's no way to connect those two, so your limit does not exist. And sometimes you have asymptotes in here. This little guy in here would have an asymptote. These two pieces of my graph will never, 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 ever meet. There's no limit there. The limit is the point that it will both approach. So that guy is not going to happen. Now, if you take a look at, some of these might be on this note page. If you kind of take a look at this, this is going to help us do our point of discontinuity here. This, if we look at this function. Yeah, but first let's talk about it for a second. Is there any value of x that I cannot use?
No. Wait, -1?
Why?
Because that's asymptote.
That would be...
No, it's like
it's a domain restriction. We're saying if we set this to 0 when x is -1, you're going to get an error, right? Your calculator should say error. So let's put this in your calculator. You're back to a regular graph. Put it in your calculator. If it's easier, use the fraction bar. Then you don't have to worry about getting parentheses in here. Okay, and we're going to graph this. Just do a zoom 6 and graph it. Now, it looks like like a line to me. It looks like there's no problems in this, right? However, when I look at my table, you see one right there. Mason found it. At the -1, it says error. So when x is -1, that point doesn't really exist. But if I come from my graph, from the left side and from the right side, will I converge at the same point? Will I be able to fill that in and remove that point? So we write this, instead of writing it like this, we write it as a limit. As x approaches -1 for this function, what would be my value? Now the easiest way to do this is when I look at my table, these are kind of far apart. Look at these two. At the -2, it's -3. At the 0, it's -1. They're kind of far apart. Yeah, I could probably realize what's happening. These are all going up by 1, right? So I could say it's -2. I could kind of see that my point of discontinuity would be at the -1, -2. Or I can fine-tune this. Now, the reason I say fine-tune is so we can look exactly what's happening around this -1. Here's my -1. If I look slightly to the left of it and slightly to the right of it, I should almost see them converging at the -2. If I look at my calculator, watch for a second. If I say find me a value when x is -1, it's going to say, nope, you don't have a value here. You can't use -1. So I say, okay, find me a value when it's real close. Bless you. When it's real close to -1. -1.0001. Can you find me that one? It says, yeah, I found you that one. It's -2.001. Pretty close to -2, isn't it? Now I'm going to look at it from the other side. I'm going to say, okay, find me the value on the other side of this guy. -0.999. And it says, oops, I found you that one too. So if I was going to meet right here, what point would that be? -2. So my limit is -2. This is a removable point. This was my point of discontinuity. It has a limit. It also, surprisingly, has a limit when x approaches 2.
Why is that again?
Which part?
That it has the limit at 2.
At 2, because the limit says there is a number there. It does exist. I can tell you where you are when you are at -2. So I'm going to look at my table, and I'm going to say, okay, here when x is, maybe, here when x is -2, what is my y value?
Right.
Yes, so it has a limit. Oh, here, make it +2. At +2, what is my y value? 1. At -2, what was my y value? So those have limits. We still call them a limit. It exists. It's there. The point is there. The point is there. And a point of discontinuity in which I can make it be continuous reaches a limit, approaches the same number. It approaches the same number from the left and the right. It can either be there, or technically I can figure out where it would have been.
I'm still confused.
Right. Because when we did discontinuities, remember we had that little point there? We say, what would this point be?
Right.
And then you reduced your function and then plugged it in. And you say, if we could circle this in, it would be this point. So I call that my point of discontinuity. It's a removable point to make my rest of my function continuous. Now the rest of the function exists. The limit is there. Every point has a y value. So it can be there, or I can make it be there. Versus not being there at all. And we'll look at one that does not have a limit. So as x is approaching -1 from either side, I know where that's going to meet. I know where it's going to be. I can look at my graph and say, that looks like there's no gap in here, doesn't it? It looks like it's continuous. So to make it continuous, find out what that little y value should be. Okay? It's a little bit different. It's a little different way to look at this. Now, sometimes we can't do that. Here's a piecewise function. Here's a piecewise. And it says, when my domain is not equal to 3, y is equal to 2. Make y equal 2. So I make a xy table. I could use -4, I could use -1, 0, 1, 2, 4. I cannot use 3. All of these have 2. So all of them dot, open at the 3, dot. If I was to fill in when x is 3, what would that y value be? To make this a continuous line. 2. So my limit as x approaches 3 is 2. I can clearly find it. Clearly see it. My limit as x approaches -1 is 2. That one, it's already there. I know it's there. It's in my table. It's there. Okay? So it can be there, or I can make it be there. Now, I don't care about this part because it doesn't affect my graph. It makes it a function, yes, when I drop a vertical line test, but it doesn't affect my making me be continuous and not having me to pick up my pencil. That's my goal, to make a continuous line without having to pick up your pencil. I really don't like to say it that way because once I asked it on the test what makes a line continuous, and a lot of kids said, making a line without having to pick up your pencil.
Do you give them credit?
Yes, I did. Because technically it's true. I just wanted them to say there were no domain restrictions, it was a continuous line, but I gave them credit. Now, this is a very different situation. If I graph this in my calculator, I get this graph. So if I'm looking for the limit when x approaches -1, if x is -1, what's the value of y? What's the value of y? You have this on your sheet.
Oh,
What's the y value for this? -1. What's my limit as x approaches 2? God bless you. It's neither -1 nor 1. Well, those two lines, it's just no limit.
No limit?
No, we can't. There's nothing we can do to bring those two things to meet at the same point. So we say, limit does not exist. We call this a jump, discontinuity. This was a point discontinuity. We could fill this in. This is a jump discontinuity. We can never make them meet. So that limit does not exist. Kind of like those step functions, there's no way to pull those together. Limit does not exist. It's kind of things we did before. We're just revisiting those using calculus terms. This again, there's no way we can ever bring this together. As I approach 0, when I want to fill in for 0, is there a y value that I could fill in for 0 to make those two functions? No, so I say limit does not exist. And I wrote you like 3 reasons when your limit does not exist. They approach different points from the left and the right, such as the one before that. They decrease or increase without bound, which is this one. And they oscillate between two fixed values, which is more like a step type thing.
What's that little B for A?
What's the what?
The little thing for the first one on limit can fail to exist. Like that little slap or different.
from the left and the right of C, you have that on your paper. It's on your paper.
Yeah, what's the little thing on? On the first
Different.
one, they're different. Yeah, what's the
Different
little
number. Oh, that says number.
Oh, it's a number. All right.
Number. They're a different number from the left and the right. Okay. Go to your homework for me for a minute. There's a homework page. All we're doing tonight is graphing. Just graphing them. We want to graph them. We want to look at your table to see if there is a point where I can get the two pieces that were not continuous to converge at the same point. I want to see if I can remove my discontinuity. If I can, then I will find a point that I can remove it. If I can't, then I say the limit does not exist. There's no way I can bring these 2 points to meet at the same place. So, what I want you to do is take your calculator. First of all, take a look at this guy. Normally you're going to tell right away if you have a domain restriction. Does this have any domain restrictions?
No.
No. So in my denominator, I can use any number that I want to, except for 0. So x cannot be 0, because at 0 you can't do this, right? You can't put a 0 in. So 0 has an open point. And I want to see if it's going to be continuous otherwise. So I'm going to put this in my calculator, in my y equals, and if it's easier, use your alpha key. Otherwise, you need a slew of parentheses in this thing. A slew of parentheses. As it is, don't forget to scroll out of those parentheses, those things. Alright, so we're going to graph this. Now, according to this, it sure looks like the 0 is covered, doesn't it? But when I look at my table, 0 gives me an error. I want to know, well, maybe I can get my window a little bit narrower in here. Let's put my y to -1 to +1. Just so that I could see what it's looking like. I'm at -1 to +1, so can you see that it's not just a straight line? Okay, I widened that part of my window. But at the 0, I can't use 0. So I want to know, is there a point that I can fill in, a point of discontinuity that I can remove so that I can get this to go? I also have restrictions in my domain because of this guy. X has to be greater than or equal to -3. This is my, oops, bear with me. This is my radical one. So if I have to be greater than or equal to -3, that's why it's starting right there. Okay? But then I threw a second one in it. Now, this is what I want you to do. You have 2 choices. You can set your table and look at your calculator, or you can do it this way. These are the most 2 important pieces that I want you to see. If I look at my table, I really can't tell what point that is. When I look here, between this one and this one, between around the 0, the -1 and the +1, it's not the same point. I need to get it closer together. So either I can table set, start at -1, start at 0, because that's where I'm going to have a problem, and increment it by 0.001, make it real close by, and now look at my table. And I could say, oh, can I now see that it's almost the same point? Isn't it almost the same point? So what's the limit as x approaches 0? 3 decimals. 0.289. Okay, that's one way to do it. Change your table. This came from the book. They give you these to look at, and then these to look at. if sometimes you need to get close, like into the thousands. There's another way to do this. Come to your graph. Come to your graph and do second calc and put a value in. Go to the left and look at that value. There it is. This is without changing your table. Second calc value. Go to the right and look at your value. There it is. So if you want to do it on your calculator rather than your table, that's fine. It doesn't matter to me which one you use, as long as you use one of them. So you're going to do that for the rest of those problems. You're looking graphically, can I remove this point? Sometimes it's a jump. You cannot remove it. You say the limit does not exist. When it does converge to the same point, then I have a limit. Okay. Another sheet that I got for you guys was this one. I thought if I just give you more visual things to look at, it would kind of like make more sense. Again, this is how we did our piecewise functions. Maybe you'll remember doing your piecewise. We usually didn't have that many. We usually had like 3. But remember how I had to label them all?
Yeah.
And then make a table? So for instance, this one just does 2 points. But this would be a closed circle. This would be an open circle. Remember these now? When we plugged in your domains? This was part of a parabola. This guy, part of a line. This guy was just a point. This one here made it a decreasing line. This guy, a constant at y equals 0. Okay, so this was pieced together. Most of all, I want to know, where is this graph continuous? So if I start here with my pencil, and I go here, do I have to pick up my pen?
Yeah.
Then this is not continuous. This is a point that it's not continuous. Is there any way I can connect those 2 points together?
No.
No. This is a jump to continuity. Okay, I'm going back. I come up here. Whoops. I have to pick up my pencil and come over here. Is this removable? Can I see exactly where that y is?
Yeah.
Ah, so what is my limit as x approaches 1?
-2.
Not negative, but,
Oh, 2.
Two.
My bad.
right? And I could plug it in. Then I keep on going.
What's
Whoops.
that black dot?
Don't worry about that black dot. I'm only looking at my graph right now. He makes this a function.
Oh, okay.
Black dots matter.
So now I jump over this. Is there a y value I could fill in to make this point removable? 0. So my limit as x approaches 2 is 0.
Same 3.
Well, that's kind of the end of my domain, so I really don't have to worry about that.
Okay.
I'm not sure if they wanted me to end up filling in or if they just wanted to end my graph there. So I really can't say that.
Okay.
Now, another point is this point over here. I'll call this point A. The limit from the positive side, as it approaches from the positive side, so the limit as x approaches -1 from the positive side exists. What is that value? This value of this y is what? 0. It exists. From the left side, it doesn't exist. There's nothing to my left. Okay? Alright, so let's take a look at what these questions are asking. These questions like kind of repeat themselves, but in a way so that you kind of think a little bit. This is my x. When x is -1, do I have a y value?
Yes.
Yes. So therefore, what is my limit as x approaches -1 from the positive side? 0. Okay. It's just asking you, does it exist? What is it? And does it exist? Oh, we answered it over here. So they kind of asked the same question. Is x continuous? Is my function continuous at x is -1? No. Well, It is only because it's an endpoint. That's where it meant us to start. So it is because of that endpoint. Is this function defined when x is 2? Do you have a value right now when x is 2? No, because it's open, right? There's no value. It's not defined. No. Is it continuous when x is 2? No. I have to jump over it. But my limit, if I should assign a value to that, what value would I assign to that value? What y value could I plug this in and fill it in? 0. So I'm going to write this, my limit, as x approaches 2 is 0. So those are the things we're just kind of like going over again and again. We're just saying, is this the limit? Is it there? Does it exist? How about this one? Is there a limit when x is 1? Here's your little dot. Is there a limit when x is equal to 1? Here's where your little dot comes in. The dot does not affect my graph. The dot affects my function, but not my graph. So if I ignore the dot, is there still a limit here?
Yeah.
There's a limit. What's my limit?
X approaching 1 is 2.
Right. As x approaches 1, yes, it would be 2. My dot doesn't play into that. It just makes it be a function because it passes a vertical line test. Yeah. This is probably good on this page. I'm just kind of jumping around. Wait, don't pack up yet, guys. This one. Is this a removable or a jump discontinuity? Jump. This is a jump. It's jumping. Is this guy right here, is B removable or a jump?
Removable.
Removable. So what would this limit be as x approaches 2?
1.
1. Good. Very good. So you're kind of seeing this graphically, what's going on? Would you understand the graphing part of it? Graphing from point to point and flipping to the table?
Barely,
All
but
right, so when we go over tomorrow.
yeah. All right.
All right, because I'll put them on that.
Okay.